Now we talk about independent random variables. So two variables x and y are independent if we can write their joint density function. So this is the joint density function of random variables x and y as a product. So as a product of density function of random variable x times density function of random variable y. So let us do an example. We have seen this example before. So the joint density function of random variables x and y is given as twice exponential of minus x minus 2y if x and y both lie in the interval from 0 to infinity, and it is 0 otherwise. So we can rewrite this as twice exponential of minus 2y. So this is just the density function of the random variable y times exponential of minus x, and this is nothing but the density function of the random variable x. So the joint density function is equal to product of individual density functions. Now we talk about expectation of the independence of functions of random variables. So if x and y are independent, then for any function h and g, so say h is a function of y and g is a function of x, and x and y are independent, then expectation of g times h is expectation of g times expectation of h. So in particular, if you have expectation of xy, this is equal to expectation of x times expectation of y. So this holds only if x and y are independent. If x and y are not independent, then this formula would not hold. So now we talk about covariance. So covariance of x and y, this is given as expectation of x minus expectation of x, and then you multiply it with y minus expectation of y. So now we just simply multiply x times y, this is xy, and then you have y times expectation of x, which comes right here. Then you have expectation of y times x, which comes here, and then you have expectation of x times expectation of y, which comes here. Now you take the expectation inside. So notice that expectation is a constant. Expectation, once you compute it, is a constant. So expectation of expectation is always same thing. That is, say expectation of, say you take expectation of some random variable x, this is always equal to expectation of x itself, because once you compute expectation, it is a constant function. So now you just take the expectation inside, so you get expectation of xy for the first term. Here expectation of x is a constant, it comes out, so you just have expectation of y. Here again expectation of y is a constant, you take it out, you just get expectation of x, and expectation of x times expectation of y is a constant. So this product is a constant because expectation of x is a constant and expectation of y is a constant. So if you take its expectation, you just simply get expectation of x times expectation of y. So now you just do the cancellation, you cancel this with this, and you get this result. So covariance of two random variables x and y, this is given as expectation of xy minus expectation of x times expectation of y. So notice that if x and y are independent, then expectation of xy is equal to expectation of x times expectation of y. So then the covariance would be 0. So in general, we will use both these formulas. We will use this formula as well as this formula, and obviously this formula is much easier to use. So covariance of xy is expectation of x times y minus expectation of x times expectation of y.